Good day everyone, we from A3 Group would like to present our case study. Coronary stents are used for patients undergoing percutaneous coronary revascularization, although the restenosis rate after coronary stent implantation is lower compared to balloon angioplasty. Stent restenosis remains as a major problem. We will start with question number 1. What causes stent restenosis? Stent restenosis occurs as a result of the response of the vascular tissue to the injury caused by coronary angioplasty after stenting. Stent restenosis can arise due to abundant healing within the stent with scarring. When a stent remains placed in the human blood vessel, many new tissue grow within the stent to appropriately cover the struts. The scar tissue may grow beneath the newly established healthy lines. The creation of such scar tissues underneath the arterial lining might become so thick that it obstructs the blood flow and causes a massive blockage. After around 3 to 6 months, patients would experience stent restenosis. In terms of mechanical causes is under expansion of the stent. During the process of implantation, the stent is too small or misaligned in the blood vessel. Stent is not properly applied to the wall of the artery. A space filled with blood can be detected between the stent and the vessel wall. Patient experience stent restenosis.
Proceed with question number 2. Suggested and describe at least 3 approach to overcome for the restenosis problem. So, number 1 is by the brachytherapy. So, for the brachytherapy is irradiate the inside of the artery directly for about 10 minutes, and this will help prevent future tissue growth of the arteries so that the restenosis will never happen again. So, for the number 2 is do the restenting. So if the stent is not properly deployed or expand properly at a high pressure, balloon should be used to re-expand the stent. So if the problem is the tissue overgrowth, so another stent should be placed. Last but not least is modular stent as a stent structure. Modular stent is the design improvement, provide the flexibility and access to the site of branches, and finally will inhibit high radial force and low rates of the restenosis. So modular stent with the closed cell design connect of all the sides. So closed cell stent will reduce the plug prolapse and increase the radius at the expense of the flexibility, compatibility, metal arterial ratio, and also the ability to access stent covered side branches.
Medical device categorization, we have categorization of nature of body contact and also categorization of contact duration. For categorization of nature of body contact, stent is implant device. Stent is a tube that is inserted to our vessels, thus it involves the blood vessel. For categorization of contact duration, long-term exposure medical, it is a long-term exposure medical devices. Stents are made to be permanent, which lasts for 15 to 20 years, exceeding 30 days. Since it is exceeding 30 days, it is a long-term exposure medical devices. Biological evaluation test. We have cytotoxicity, sensitization, acute systemic toxicity, hemocompatibility, material-mediated phylogenicity, irritation, and many more. So I will go through one by one. For cytotoxicity, it is used to determine the cell death, the inhibition of cell growth, colony formation, and other effects on cell caused by medical devices. Sensitization used to estimate the potential for contact sensitization by medical devices. Acute systemic toxicity. Acute systemic toxicity test can be used where contact allows potential absorption of toxic leachables and degradation products to estimate the potential harmful effects of either single or multiple exposures during a period of less than 24 hours to medical devices. Hemocompatibility. This test used to evaluate using appropriate model or system the effects of blood contacting medical devices or material on blood or blood components. For material-mediated pyrogenicity, these tests are intended to detect material-mediated pyrogenic reactions or extracts of medical devices or materials. Irritation tests used to estimate the irritation potential of medical devices, material, and or their extract. Chronic toxicity used to determine the effects of either single or multiple exposures to medical devices during a major period of the lifespan. Implantation effect can be used to assess the local pathological effects on living tissue at both the gross level and microscopic level of a sample of a material. Carcinogenicity. Evaluating carcinogenicity of medical devices over a period of the major portion of lifespan. Subacute and subchronic toxicity tests can determine the effect of their single or multiple exposures or contact to medical devices, materials, and or their extracts for a period not less than 24 hours to a period not greater than 10% of the total lifespan. Genotoxicity. It is used to assess the potential for gene mutations, changes in chromosome structure and number, and other DNA or gene toxicities caused by medical devices, materials, and/or their extracts.
Question 4. Imagine that you are the junior biomedical engineer responsible for developing a new coronary stent. Propose design considerations for this device. Design considerations should include chemical, morphological, mechanical properties of the biomaterial that will be used. The first chemical that will be used in coronary stent is cobalt chromium. Cobalt chromium is a metal alloy. Molybdenum produces finer grains which result in higher strength. Chromium can enhance the corrosion resistance in the blood under the coronary contraction. Cobalt chromium alloys has no significant toxicity to the human body. The second chemical that will be used in coronary stent is polylactide or PLA. PLA with the formula C3H4 O2 is a monomer lactic acid. It has biocompatibility and biodegradable properties compared to the metal coating, and it polymerates buffer for drug delivery, and it is biocompatible and non-toxic.
Then I will present to you about the consider in the morphology property why we choose the cobalt chromium as the material in the body of the stent. First, the cobalt chromium has a high radioopacity similar electronegative. With this property, the thinner strength around the 18 to 19 mm of the stent can be produced while retaining the model radioopacity. This allows the strength structure to be tolerant and improve the flexibility. This can reduce the bacterial ingress during the implantation and reduce the restenosis occur after the implantation. Secondly, the cobalt chromium can provide the modular strength. The modular strength can provide the flexibility and access to side puncture, and finally will inhibit the radiant force and low depth or restenosis. The consider in the morphology property why we choose the polypeptide is polypeptide shows the excellence because ratio, and the polypeptide has the excellent surface coating durability at the body of the strength. Next, the consideration in mechanical property why we choose the cobalt chromium is cobalt chromium has the high modulus, young strength, tensile strength, and density. This cause the material has the superior radiation impermeable and radiant strength. The hardness of the cobalt chromium is between 145 to 270 megapascal. The tensile strength is around the 1782 megapascal. The yield strength is about 1585 megapascal. The elongation is around 8%. The next consideration in the mechanical property why we choose the polypeptide is polylactide is biodegradable coating polymer. Excellent for the delivery to prevent the restenosis, and the rest or inflammation approach the polymer degradation is low. The polypeptide with the tensile strength 69.91 megapascal, yield modulus with 1568 megapascal, and elongation 3.8%. In conclusion, the development of the new strength with thinner structure and covered with the biocompatibility and biodegradable formula can present an important improvement for the stent, especially for reducing of the restenosis rate. This is all presentation today. Thank you for your watching. Bye bye.